Okay, today we're gonna talk about algebraic topology, and one of the most important concepts in algebraic topology. This is the fundamental group of a topological space. There's a joke in mathematical community that topologists can tell a mark apart from donut. This obviously is true. Why? Because let's see here. As illustrated in the figure, we have a continuous map from a donut to a mark, and the inverse map from a mark into a donut is also continuous. Uh, Two spaces that have a continuous bijection with continuous inverse between them is called a homeomorphic space. So a donut is homeomorphic to a mark in this case. So this is why topologists can tell a mark apart from a donut. Now a question arises: how do we tell two spaces apart up to homeomorphism? Uh, In 19th century, Henry Poincaré have an idea. How about we consider a loop in topological space? Now, let's consider this topological space X, ugly looking dog-shaped space. It doesn't matter. Uh, Now, this pink loop can be retracted into a point that is a constant loop. However, that's not the case for the green and the yellow one. There's a hole blocking us in the way. So this inability to retract or to continuously deform some deform a loop into a constant loop is telling us some information about the topological space it lives in. In this case, the existence of a hole. Now, this continuous map between a loop into another loop is called a homotopy of loop. Now, we can make a collection of every loops on a topological space that's based on a point. In this case, we call it x0. This is the mathematical definition of the operation. However, we can interpret this as this. Imagine a loop is just you going around something in 1 unit of time. Now, concatenating two loops means you are joining two loops together. It means that if we want to preserve our time, 1 unit of time, then we need to go twice as fast and on the first one and twice as fast on the second one. So on the first one you go half a second, and on the second one you go half a second. So in total you still spend 1 second or 1 unit of time, if you will. Now this operation is not associative, sadly, uh, and it will be better if it's associative, right? Uh, we want it to have a nice algebraic property. Even better if we can make something like a group out of this. So now, how do we solve this issue? Now, notice that this is a loop. This is a loop. The only problem here is only on the parameterization. So, how do we solve it? By the means of homotopy, of course. Homotopy turns out to be a really strong tool in this case. So, we say that the operation is associative up to homotopy. And of course, it has a reason. Uh, the homotopy gives rise on an equivalence relation on the loop space. So we can now just quotient out the loop space with the homotopy relation. Eventually, this leads us into a group called a fundamental group, which contains a class of loop on the topological space up to homotopy. I give several examples here, uh, which I will not go into detail, obviously, because it will take too long and it's complicated actually. But this is the most useful property. This means we have a very strong algebraic invariant that we can use to characterize topological space up to homeomorphism. And that's it. Thank you.